The question is, a DC motor is constructed from a single loop of wire with dimensions so and so. The magnetic field strength is 0.40 Tesla and a current of 14 ampere flows through the loop. So the best thing is to start writing everything that is given to you. It's a DC motor, and there are a lot of parameters given there, or values. So number of turns is equal to 1. And what are the dimensions? So dimensions are given definitely to arrive at the area, and that should be equal to 0.10 multiplied by 0.07. So this should be equal to 7 into 10 to the power of minus 3 meters square. And B, magnetic field intensity, is given as 0.40 Tesla and a current of 14 ampere. So a DC current of 14 ampere flows through the loop. So part A of the question. So part B we'll see a bit later. Calculate the magnitude of the maximum torque produced by the motor. So for that we need to know the formula of the torque. So if you remember the expression for the torque, so the magnitude of the torque, because the question says only the magnitude, so that is written as NBIA sine theta. And what is theta, if you remember? So theta in this case is the angle which the normal to the area makes with the vector b. So in this case, in this figure, we have, this is the plane, so maybe I can label it as A, B, C, D. So if I draw a normal to the plane, so it will be something like this, normal to the plane. It's not very good drawing, but I think we can manage. So the normal to the plane, and the angle that it makes with the vector b. Yeah, so this is area vector A, and this is vector b, magnetic field. What is the angle between the two? So theta is 90 degree. So theta is 90 degree, and sine theta, we know it will be equal to 1. So that, but the question says what is the magnitude of the maximum torque? So in fact, we need not have gone into the value right now. We can, as far as the maximum torque magnitude is concerned, we know that torque maximum. So the expression for torque here, this is representing a sine curve, where this is the magnitude of the sine curve, and of course because of this we have the sine curve, sine theta. So torque maximum will be equal to NBIA. And if we put the values simply, so it should be pretty easy. So 1, and B is 4 into 10 power minus 1 Tesla. I is 14 ampere. And A, that is the area, so that is 7 into 10 to the power of minus 3. So it's a simple multiplication, and that should give you the answer. So let's see what is the answer. To be able to complete the answer, we will do the calculations. So 28 multiplied by 14 into 10 to the power of minus 4. Yeah, and what is the unit, if you remember? So this will be Newton meter, because that is force multiplied by, so that comes to 392. In the interest of time, we can, because I'm not so much interested in showing the multiplications, I just need to come to the correct answer. So into 10 to the power of -4, and which can also be written as 0.0392 Newton meter. Yeah. So the part B describe how the magnitude of the torque changes as the loop moves through half a rotation from the position shown. So the position that has been shown in the picture, as we discussed in part A, is representing theta equal to 90 degree. And we are, a full rotation will be 360 degree, and in the question it says half a rotation. So from theta equal to 90 degree to 90 plus 180, that is 270 degree. So if the coil is so before that, before we go into it, let's see the direction of the torque. Yeah. So if I label it as A, B, C, D points on the coil, and we see that at this position, at the initial starting position, when theta equal to 90 degree, the direction of the direct current is like this. Yeah. If we focus only on the segment of the coil which is AB, so we see that current is going into the page, yeah, and magnetic field is towards the right. So if I draw it, so that we have to find out the direction of the force, yeah. So what is the direction of the force or the torque? So when you torque is given as, maybe I can write the expression, the force experienced will be equal to L times I cross B. So we write it as vectors, although current is a scalar quantity, but we can write as an expression current in the form of a vector, and this will be equal to LIB sine theta, where theta in this case is the angle, smaller angle between I and B. So when we, if I put a screwdriver at this point P and rotate the screwdriver through the smaller angle, yeah, if I rotate through the smaller angle from I to B, I am rotating through 90 degree, yeah, and the rule says, the right hand rule says that you have to see the direction in which the screw, if you keep at P, will advance when I move the screwdriver from I to B through the smaller angle. So it says it will be moving into, so moving down, yeah. So the direction of the screw will be in this direction, of the movement of the screw will be in this direction. So force experienced will be in this direction. So this point P is same as A in our discussion. So if you see what will be the force over here, it will be, force will be acting down. Okay, so acting down, that means the coil will try to rotate anti-clockwise, yeah. And the expression for the torque, we have to, the magnitude of the torque is given as NB IA sine theta. So this theta is the angle which the normal to the area makes with magnetic field B. So both theta are different, so don't get confused. So in the question, he is asking to plot the torque with respect to the angle theta. So taking theta on the x-axis and the magnitude. Yeah. Not a very good graph, but let's see how best I can draw it. So this is theta and this is torque. So we have to start, since the initial position is given as theta equal to 90 degree. Yeah. So theta equal to 90, and then this will be 180, and this will be, add another 90 to this, 270, and finally add one more to make it 360. Yeah, so we have to plot it from 90 degree till 270 degrees. So at theta equal to 90, sine theta will become 1, and therefore torque will be equal to torque maximum. So torque equal to torque maximum, whereas the value of torque maximum is the one which we already calculated as part of part A. So at theta equal to 90 degree, that is the starting position. So it will start rotating anti-clockwise, and maximum torque produced over here, and it will follow the sine curve. Yeah. So what is the sine curve? So if I put this as the maximum value, so it will be something like this. So at theta equal to 180, so it will be sine 180, and sine 180 is 0, and therefore the torque will be 0. And going forward, we know how the sine curve moves, and therefore sine at the value theta equal to 270, so that will be equal to -1. So maybe if I can show the minus y-axis, it will be something like this. Yeah. And then of course we know it is a sine graph, so it has to go something like this. Yeah. And then we can extrapolate this further. 360 plus 90 will be 450. I don't have to draw this, but let's, for the sake of completeness, do it like this. So this is the torque max, and this is minus torque max, and this torque equal to torque max into sine theta. So in the question he is asking only for half a rotation. So half rotation will be ideally we need to draw only till this point. Yeah. So this will be the graph. So it starts with the maximum at theta equal to 90, becomes 0 with theta equal to 180, and then goes in the negative direction and becomes maximum at 270 degree. So this is more from the graphical representation. Let's see what is happening on the coil actually. So as soon as the side C and D goes up, that means it completes the quarter of the rotation. So the commutator, let's call it as C1 and C2. So this commutator, when the coil comes up, this commutator will get in touch with the brush over here. Yeah. So maybe I can label it also as B1 and B2. These are the conducting brushes. So at 1/4 of the rotation, the coil side CD will be positioned in such a way, or the commutator will be in such a way that C2 will get in contact with B1. And the moment that happens, there is a change in the direction of current in the coil. And therefore, maybe I can show it. If you change the direction over here, yeah, at 1/4 of the rotation, there will be, again, if you apply the same logic of finding out the direction of the force, you will see that the CD will continue to rotate anti-clockwise. So just to summarize, at 1/4 of the turn, the current is reversed with the help of commutator so that the torque continues to be applied in one direction only, yeah, and therefore resulting in a anti-clockwise direction. So that explains, we may not go in our answer in so much detail about describing at each 1/4. We need not put it into so many words, as the best part is that if we are able to explain it with this graph, that should serve the purpose. That clearly shows, yeah,